the pleasure to have our last wild session with Guy, as it was announced, so take it on.
Let's see. Okay, I stored my notes, so let's see how that goes. So, yeah, I wanted more time to go wild, but I still need to finish my responsible duty as an educator. So I will continue systematically for at least the next half hour. So I want to give you a feel for the singularities. Of a cosmological correlator. Okay. So I will go to flat space and forget about cosmology. So our cosmology is flat space. So, but what I will do is instead of computing a scattering amplitude, I'm going to compute the in correlator or the wave function of the universe in flat space. So I take a time slice. So that's not what we usually do in scattering amplitudes. In scattering amplitudes, we work with on-shell states. So they are at infinity. You send them in, they scatter. You have some outgoing states. While here, we take some time slice. Let's the actual location of the time slice doesn't matter. So let me set it to be 0. And then I'm going to compute either the wave function, depending on the propagator that I use, or the in correlator. So, I mean, we get more or less the same lessons from both, but I'm going to focus on the wave function. So, for example, if you take phi cube theory, this will be the wave function coefficient. And the propagator, this is just the bulk to boundary propagator, the one I introduced to you just before you had lunch. This is T. It's just given by this formula, e to the I omega t. So it's very, 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 very simple. And I have 3 points, 1, 2, 3. And as usual, omega is square root of k squared plus m squared. Okay? Very good. So the wave function coefficient, so now the wave function of the universe is going to have a Gaussian part, exponential, minus integral d3k. Then it's going to have a Gaussian part, phi k1, phi k2, psi 2 of k1, k2, plus ta ta ta. And this is the diagram that computes psi 3. Okay? So the diagram that computes psi 2 is just the thing we've been studying quite a bit throughout the lectures. And this is for psi 3. So this is very simple. So what you do, as usual, so there's some coupling constant, it's phi cube theory. Coupling constant is not very interesting, just to put G here. So psi 3 is going to be G, and there's a time integral, okay? So usually at 3 level, there is no integration to do. Everything is trivialized in flat space. But in cosmology, even at 3 level, there's one integral to do, which is time evolution. So we're going to integrate from minus infinity to t star, which is 0. E to the product of the propagator. So there's propagator 1, propagator 2, k1, k2, k3. So that gives us e to the I omega 1 plus omega 2 plus omega 3 times t. The spatial part, you integrate over the whole slice, just plane waves, e to the I. So okay, I'm going to do it just once. You integrate over space, d3x, so this is integral over time. And you integrate e to the I, k1 plus k2 plus K3 X. So this gives me a delta function, our very old friend delta function. So this is always going to be there. And okay, this is not very interesting. We're going to strip it out because of translation invariance. And if we were doing the integral from minus to plus infinity, this would give us energy conservation. Okay? So this would have been delta of omega 1. Alas, it's not, because we're integrating from minus infinity to 0 instead of from minus to plus infinity. And, well, okay, so we do it the way we learn in our first calculus course. We find the primitive, we evaluate the primitive in the n intervals, and you do the I epsilon prescription to kill the boundary term at minus infinity. So this is the answer. So it's a delta function, delta 3 of K1 times G divided by, okay. So we learned something. We learned that the flat space wave function, it has a singularity, okay? So usually 3-level scattering amplitudes are analytic. Here, even 3-level correlators are non-analytic. They're meromorphic. They have a pole. The pole is not visible in the physical region because you're just adding up a bunch of positive things, right? But as we know, every square root has a cut. You can go around the cut, and then you make omega negative, and then you can access the singularity. And then when you take the limits and you access the singularity, omega 1 plus omega 2 plus omega 3 equals 0, you're sitting on the support of the energy conserving delta function. So this blows up, it blows up, and the coefficient is G, the scattering amplitude, okay? So now you're not very impressed with this calculation because, but I claim this is a general phenomenon, okay? So then there's some theorem. I'm not a mathematician, I'm just bragging, okay? It's theorem. So if you take any correlator, 1, 2, 3, 4, 5, n, and you take the limit, sum over I, omega I to 0, of the wave function, it's going to blow up. In flat space, it always blows up like a pole. In cosmology, the singularity might be of a different nature. It can be a cut. It can be higher order. So I'm just going to write it like this. But and the coefficient of the leading singularity is the flat space scattering amplitude. Okay? So this is true in any cosmology. If it's curved space, it doesn't matter. And why? Because when you send the sum of the energies to 0, from the point of view of this integral here, you're killing exactly the thing that was responsible for damping the integral at early times. So you're making the whole process peak at such early times that all the cosmological fluctuations don't even know that they're in curved space. Okay? So that's it. This is the physical intuition. There are proofs of this. It works for any correlator. And there's a beefed up version. So this is the first part. And the second part of the statement is that if I take 1, 2, m plus 1, n, if I take now the limit where I send the sum of these energies to 0, so limit sum, omega 1 plus plus omega m. Let me call this exchanged particle to have k intermediate plus omega intermediate to 0, okay, of psi. I get some blow up again, 1 over omega 1 plus ta 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 plus omega intermediate. And I get a bit of a Frankenstein multiplying it. The Frankenstein is the flat space amplitude for this process. So I get m flat for 1 to m going into intermediate times, and this time requires some fine print that I don't have the time to go over. It's not multiplication, okay? It's some multiplicative like operation times the wave function I m plus 1 n. Okay? So you get products of flat. So here you're forcing all of these particles to be blue shifted. Okay? So you need to account for the fact that this guy propagates and it becomes an incoming state. So that's why this requires some elaboration. But the important thing, what do you get from this? One is you can relate the cosmological correlator to flat space amplitudes. Another, the cosmological correlator. So this is the connection to amplitudes. And this one is factorization, which is the usual avatar of locality in particle physics in an amplitude. So you can relate the n-point function by taking these limits to lower point data, right? So this is the flat space amplitude at m plus 1 point, and this is the wave function at n or whatever, the number, you can figure out the number of points, okay? Questions? It's the same reason. When you do these integrals here, there will be propagators and there will be various integrals to do, so there will be, you know, there's going to be some collective time, which is the time that you move up and down the whole process. Then, so you can change the time all the time coordinates, go to the center of mass frame of there's one time that is common to all of these propagators, and then argue that what multiplies that time is the sum of the energies that flows into the blob. So when you send this sum to 0, you send the whole process to the past. Okay? So that's it. So let's see how this works out in the next to simplest example, which is 4 points. I go 1, 2, 3, 4, and I go to the S channel. So there's, so I tell you the answer, and then you immediately believe that I'm telling you the truth. The honest way of doing it is you have, you know, so I'm going to write the formula. I'm going to tell you the result. So what's the formula? There's two integrals. There's integral over T1 and T2. T1, T2. There's a propagator for momentum 1, T1, propagator of K2, T1. Then there is this bulk-to-bulk propagator of momentum intermediate. So this is the intermediate momentum. Of course, and very importantly, this is not equal to this. Okay? Right? So you just multiply all the propagators, and there is this bulk-to-bulk propagator. It has 3 terms. It has the Feynman propagator, and it has this rule that the propagator should vanish as I approach this time of observation. And there's a g squared for good measure here, because there's the coupling constant. And here's the answer. So the answer is g squared. It's very nice. K1 plus K2 plus K3 plus K4. Sorry. Should have said omega. sorry, apologies. Omega 1 plus omega 2 plus omega 3 plus omega 4. Omega 1 plus omega 2 plus omega intermediate. Omega 3 plus omega 4 plus omega intermediate, okay? There are three terms that come from doing the nested integrals for each of the terms in the bulk-to-bulk propagator, and they add up. I mean, each term is a bit ugly, and they get married together, and they form this beautiful structure here that has the singularities that we expect, right? So there are three singularities. You send the sum of the energies of the whole process to 0. You take the sum of the energies flowing into this vertex to 0, or you take the sum of the energies flowing to this vertex to 0, okay? Now you can go and sit on the poles and see what happens. So let's do it. When you send the sum of omegas to 0, this guy here becomes minus omega 1 minus omega 2. So you get this thing here will become minus omega 1 plus omega 2 squared plus omega I squared. And I actually, if let me write it like this, ki squared. So what is this? It's the Mandelstam, right? If you build a fictitious four momentum, omega 1, k1, so this squares to 0 because omega squared plus k squared. Yeah, let's talk about massless particles for now, not to confuse ourselves with massive particles. So this guy squares to 0. Then P2 squares to 0, and the Mandelstam, which is P1 plus P2 squared, is given by this formula, right? It's the minus the 0 component, which is the sum of the energies, plus the spatial component, which is the intermediate momentum. So it becomes exactly G squared over S, which is the flat space scattering amplitude, okay? And when you sit on one of these guys going to 0, you will see that you can break it down into two terms that are related to 3-point amplitude times a 3-point correlator. Okay? So this formula also can be written in an interesting way. So this has the singularities that we expect, and now there's something really neat about this formula that I can't resist to tell you about. This is a bit of a parenthesis, but maybe we come back to it depending on how my time management is going. Let me go to massless particles, okay? So omega equals k. So again, this is 1 over k1 plus k2 plus k3 plus k4. k1 plus k2 plus k intermediate. K3 plus K4 plus K intermediate. And now what we can do is, this is an S-channel diagram, 1, 2, 3, 4. We can go to kinematic space, so there are the momenta K1, K2, K3, K4. K intermediate is here, K1 plus K2. It's K intermediate, right? So we can talk about the dual graph. You take the midpoints and you connect them, like this. And ta-da, it looks exactly like this diagram, okay? It's now, the other ta-da moment is that if you compute the perimeters, perimeter of this guy, perimeter of this guy, perimeter of this guy, multiply them, you get this answer. So this is 1 over the product of the perimeters of the triangulation. So there are three triangles, three polygons. The overall polygon has perimeter K1 plus K2 plus K3 plus K4. Then the sub-polygons are these guys here, K1 plus K2 plus Ki. This is K3 plus K4 plus Ki. So I claim this works in any graph for this model. So let's do the next one. And then I hope you'll be impressed because it's pretty cool. So let's do this example. 1, 2, 3, 4, 5, okay? So we go to kinematic space. 1, 2, 3, 4, 5. Propagator between 2 and 3. Propagator between 3 and 4, 5. Okay? So this is kinematic space, this pentagon. Now if you look at the dual graph, if you connect the midpoints, so you get maybe okay, the same graph. Okay? Now, how do you triangulate this? There are two ways. Way number one is, it's not very deep what I'm going to say, okay? You do this. Way number two is you do that. That's the first step. And then the second step is you do the opposite. 1, 2, and you get okay. So those are the two ways of triangulating. And now you multiply for every way, you multiply all the perimeters that you end up with. Okay, so let's see how that goes. So what's common to both ways? Well, the overall perimeter is common to both, and the individual triangles common to both. The only thing that the one route has that the other doesn't are the quadrilaterals. Okay, so this one has this quadrilateral here, while this one has this quadrilateral here. Okay, so let me give some names to these things. So this is of course K1, K2, K3, K1, 2, 3, K3, 4, 5, K4, K5. Okay, so there are 9 terms. There are 9 terms, right? Because you need to take the product of 2 propagators and you need to do 3 time integrals. And we just write down the answer. Let's see. So psi 5 equals. The overall, so what's common to both of them? Overall perimeter is K1 plus K2 plus K3 plus K4 plus K5. Then the little ones are K1 plus K2 plus K1, 2, 3. K3 plus K1, 2, 3 plus K3, 4, 5. K3, 4, 5 plus K4 plus K5 times this term here is K3 plus K4 plus K5 plus K1, 2, 3 plus 1 over K1 plus K2 plus K3 plus K3, 4, 5. Okay, so that's it. That's the answer. Okay, and G cubed. So that's kind of cool, no? So it works. So you can go home or on the subway back to the hotel. You can draw your favorite polygon, start triangulating it. multiplying and summing the perimeters, and you'll get the wave function. So the wave function has a lot of structure compared to the individual propagators. Okay? Yeah.
Thank you. So, considering this type of triangulations, could you, in principle, compute something like the Euler characteristic, and would that give you some information that is important? Or not?
Maybe. Let's see if I can say better than this. Maybe. Let me,
Okay.
I mean, these in the end are, yeah, I think it might teach you something about the number of terms that ultimately appears. There is something even more geometrical that screams of Euler character that appears later. But when you talk about the cosmological version of this, remember, this is very beautiful, but very simple, because we're doing the flat space wave function, so there's no cosmology here. Now, when you put this diagram on a curved with scale factor, then these functions become much more complicated, but some beautiful geometric structure arises. And when it arises, there are all sorts of things that scream Euler character. But I don't know how to put them in this. I don't know what the Euler character of is, and okay, I can show you. There are many things that scream of geometry. That yeah.
Okay, thank you.
Okay. So yeah, maybe there are two directions in which I can go wild. I wanted to go in a different direction, but maybe if you guys like this, I can tell you something related to this, which is a little more crystallized. The other thing is related to spin. This related to these things called twisters. But anyway, let's see. But I still need to be responsible and go back to cosmology. Okay, go back to cosmology. I need to tell you what happens. So we have this diagram that involves this. This is the conformally coupled scalar. Okay. Let's go back to the case of the massive exchange. Mass m spin 0, while these external guys have m squared equals 2h squared. So psi4, strictly speaking, has some decay as I send eta star to 0. So it decays like eta star to a certain power times some interesting function. And I claim that this function is essentially pinned if you impose two things. One is that it's de Sitter covariant. So you need to understand consequences of the de Sitter symmetry on this object. And two, it has only singularities where we expect them. Okay? So let's see how this works. Let me tell you what the kinematics implies. So the wave function, the constraints from conformal symmetry, from the Sitter symmetry on the wave function imply that it transforms. So this is the whole thing about ds-CFT. So psi4 transforms kinematically, okay? There is no DSCFT. As O for delta equals 2, J equals 0, okay? So you can impose the same constraints of correlation function in a CFT of a conformal primary of dimension 2 and spin 0, okay? So of course we know how to do that with our hands tied by now. You go to cross ratios. But cosmologies like comoving wave numbers. So you work in momentum space. You don't work in position space. So the nice thing about working in momentum space is that it connects to the way cosmologists like to think about these correlators, and it makes this connection to scattering amplitudes very clean. But you pay a price that you cannot impose in a straightforward way all the consequences from conformal invariance. So let's see how far we can go. So this, I'm just going to state facts. I'm not going to prove anything. So it's a moment of faith. You believe what I'm going to tell you. So this is a function of 12 pieces of data, right? The 3 momenta of the 4 particles. Now, because of translation invariance, oh, this is easy. We get rid of 3 of these. And because of rotational invariance, you get rid of 3 more. And a useful basis, and I always draw this terribly, so let me try again. Failing better every day, so let's see. A good way of drawing this is as follows. Right, okay, that's not so bad. 1, 2, 3, 4, S and T, okay? So 4 momenta, they go off the board. They're not planar. And then there's the S diagonal and T diagonal. So we can talk about, there are 6 functions that survive, 6 variables that survive because of rotational invariance. And it's useful to talk about the energies and the exchange momenta in the S and T channel, okay, these planar variables. So far so good. We impose 6 constraints. Now we use time translation symmetry or rescaling symmetry. And here, because we are in the S channel, it makes sense to pull S as the unit with which to normalize everything else. So I'm going to pull S dependence up front. And it's a little counting exercise, which, because I've done it a million times, I know the answer. But trust me, it's nothing very complicated. You have a function of this, K1 over S, K2 over S. Now, remember that I said that when you exchange a spinning particle, there is dependence on the T Mandelstam, right? In the previous lecture, when I have scattering amplitude on the S channel, it was G squared over S minus M squared times Legendre polynomial that went like T to the J, right? Where S and T are different objects, they're the Mandelstams, but they have inside of them the exchange momentum S and the exchange momentum T. So if you're exchanging a scalar, there should be no T dependence. So this is a dynamical assumption. There's only scalar exchange, okay? So it's because I'm focusing on that diagram. No, because S doesn't have the same units of Mandelstam. So S is the absolute value of K1 plus K2. So it's as the units of momentum. Yeah. Yeah, that's confusing, sorry. So Mandelstam has units of k squared. So Rogério's question is, this has units of, this is like P1 mu, P2 mu, so units of momentum squared. So we usually, to avoid this confusion, write S flat. So this is the flat space Mandelstam. Well, here I'm just talking about momenta. So I'm down to 4 variables. And then you have 3 boost symmetries to impose. And it turns out you can get almost to the end. You can use 2 of them. You can diagonalize 2 of them. One over SF of. It's not very difficult to convince yourself that this is a good ansatz. Because remember, the mode function goes like eta e to the I k eta, right? So when I multiply these 2 bulk to boundary propagators, K1 and K2 don't appear separately. They only appear in the sum, right? You multiply e to the I k1 eta, e to the I k2 eta, they attach to the same time, so they always appear added up. They always appear as K1 plus K2. So therefore, it's natural to expect, and it is true, that this should depend on K1 plus K2 over S, and K3 plus K4 over S. Okay? And this diagonalizes 9 out of the 10 isometries. The 10th one imposes a differential equation on this function. So this I cannot go further without writing a differential equation. It's just kinematics, okay? There's no, I mean, there was a little bit of dynamics when we threw away the T dependence. So there's a little bit, tiny, like a little bit of salt of dynamics, okay? So now, just to mess up with your brain, I'm gonna call U S over K1 plus K2, so the opposite of what I was drawing, of what I was writing. And I'm going to reinvert again. Sorry, I just one paper is written like this, the other is written like that. So I can't be consistent in notation and write correct equations. So to do how it's hardwired in my brain. So it turns out that this function f, by the way, I've been calling f, but it's clearly not the same f, right? It depends on 6 variables. Now it depends on 2. So okay, mathematicians would be very, very upset with me. So this function of u and v must satisfy delta u f equals delta v f with delta u equals u squared 1 minus u squared d2u minus 2u cubed du. Okay? So there's a second order differential operator. It's because boosts, they depend on second derivatives of the momenta. And any function of u and v that solves this equation, so it's a PDE in u and v with this hypergeometric-like operator, is fair game, okay? So if you exchange scalar elephants at 20 loops, then it satisfies this. So we haven't put in yet the 3-level assumption. And the 3-level assumption comes from a very simple idea. So you see, let's go back to the flat space amplitude. So the flat space amplitude is given by this formula. But this is like the Klein-Gordon operator, right? What's in the denominator. So you can write the flat space amplitude as a solution of a trivial algebraic equation. Of this form. So the flat space amplitude m flat forget about spin for now, solves s minus m squared m flat equals g squared. And g squared is just contact interaction, right? Lambda phi to the 4, if I call lambda g squared, that would be like a contact interaction. So s minus m squared is essentially the operator that kills the propagator. But because I can boost to the center of mass frame and so on, it's an algebraic equation. It's trivial to solve. The only non-trivial bit is where to put the I epsilon here. But okay, so that's it. Okay? So I will convince you in the next 5 minutes that delta U is like S. And of course, is like is very precise, but I will S flat. But I will try to make a little bit of a better argument than is like. So let's see. So for this, we need to stare at some data. I mean theoretical data, the theories type of data, not the one that nature gives us, the one that we produce with pencil and paper. So let's produce some theories data. Let's start with the simplest possible example, which is lambda phi to the 4. So these are conformally coupled scalars with a conformal invariance interaction. So why isn't it just the amplitude? Everything's conformal. Lambda phi to the 4, m squared phi squared with the right value of the mass. Why isn't it exactly like the amplitude? Why isn't the answer delta 4 times lambda? Yes, therefore, the integral over time, right, is different. So instead of integrating from minus infinity to infinity, integrate all the way to 0, e to the I, k1 plus k2 plus k3 plus k4 t. So it's just like the example that we did in flat. So, but this is true in DS. But you're not very impressed because it's the same computation as in flat space. Okay? So let's just write this in this form. So you can rewrite this. So like this function doesn't look like f of u and v, but it is. Okay? You write as lambda over s, 1 over k1 plus k2 over s, plus k3 plus k4 over s, which is lambda over s, uv over u plus v. So this function here, you can pull Mathematica, people on your laptops, and you can write, you can check that this is true for this function. Okay? It's non-trivial. You can check that it satisfies this equation. Okay? Now, when we sit on the total energy pole, it gives the lambda scattering amplitude. Now, say you want a different type of contact interaction. Of course, you can write phi to the 4, you can write d phi to the 4, you can write zillion derivatives, axiom 4 phi's. In other words, at the level of scattering amplitudes, you could write lambda, you can write, g over some mass scale to the 4th times s squared, s flat. So you can write all sorts of amplitudes with effective field theory, with irrelevant operators, right? So how do you generate cosmological correlators of irrelevant operators? So you need to build other solutions of the kinematic equation that have singularity only when the total energy goes to 0. Because there's only one time in which fun stuff happens. So for contact interactions, only allowed singularity, and this is a tough constraint, only allowed singularity at, here, this sum going to 0 is u plus v going to 0. Okay? So how do you build other, okay, I give you one. I give you one. I'm very kind. Here's one. Do you know how to build another one without no Feynman diagrams to be harmed? So how do you build another solution of my constraint? So I want some object that only blows up when u plus v goes to 0, and I want it to satisfy this equation. And you can check. You can't check in your brain, but you can check with a bit of pencil or paper or mathematical, that this function solves this equation. So how do you build another function that solves this equation? It's very simple. If I tell you the answer, you're going to be, oh, I knew it. Do you understand the puzzle? You like, some people are blue screen staring at me. So the puzzle is, I want a function that solves this equation, this PDE, very hard, partial differential equation, scary. But it can only be singular when u plus v is 0. And I give you one example, this one. So using this example and the PDE, can you build other solutions of the equation? Yes, yes, yes. Let the students. Yes. That's the right answer. But, what do you think? What would you do? Powers of this doesn't work because a second order operator. So it's the right spirit, but it's not powers of that. It's powers of something else. Yeah. It's not going to work, and it's going to have another singularity at u equals v, right? U squared minus v squared. So you cannot add a new singularity. Do you want me to tell you the answer, or you want to think? I give you 30 more seconds. Because when I tell the answer, you're going to be very frustrated that you didn't figure it out. This function here, I hit this guy with two derivatives, so it goes like u plus v cubed. There's no other singularity, and it produces some complicated numerator. Does it satisfy the constraint? It does. No, delta u commutes with itself, delta v commutes with delta u. So delta u to the n acting on this function solves the equation, and it only has singularity that u plus v equals 0. So that's it. So now let's do the simplest example. You take delta u, hitting on that. It goes like u plus v cubed with some numerator, and the numerator is kind of, I don't remember what it is, but when you send the total energy to 0, it goes like so. It goes like 1 over k1 plus k2 plus k3 plus k4 cubed. Notice that it's dimensionless. Oh, it's just some ratios of momenta. Just some ratios of momenta. But when you send this to 0, because this is a higher power singularity, you get an object up front that has units. And what is this object? I write it like this. Minus k1 plus k2 squared plus k1 plus k2 squared. What is this? S flat. Okay. So that's how you see units appearing in flat space. So there are units of the highest power of the total energy of the process. So if I give you, so that's an interesting thing. So in amplitudes, irrelevant operators make amplitudes grow very fast in the UV. Cosmological correlators, they are equally sensitive to all operators, whether they're relevant or irrelevant. What happens is that they're suppressed just by an order 1 coefficient. The coefficient up front is just Hubble divided by units of the cutoff. So there's going to be some mass scale that suppresses this operator. But it's not that as you go to higher energies, it blows up. It's always scale invariant. You only see a blow up if you go outside of the physical region. Okay? And okay, now you can do delta u squared. You're going to produce an even longer numerator with u plus v to the 5th. You sit on the pole, and you find S flat squared. So I hope now you're on board that delta u is like S flat. Okay? So now we're ready to write the exchange differential equation. Exchange differential equation. Remember, exchange for flat space was like S flat minus m squared times the scattering amplitude for exchange equals g squared, which is like some contacts-like interaction. So what do you suggest? So what is the analog of everything in this formula? So okay, so the object is our function, f of u and v. What goes as a source? What's the analog of this for us? What is the analog? This is lambda phi. This is the scattering amplitude for lambda phi to the 4. It's just that lambda is g squared, okay? So what is the object I put here? Echo. uv over u plus v. G squared. Now what goes here? Very good. This is essentially the right answer. The only thing is that m has units. This is dimensionless. So what should you put instead of the mass? What's the dimensionless object we can build in the Sitter space? M over h. And if you do things very carefully, the answer you get is this. Remember from the first lecture that funny minus 2, it comes back. So this is the answer. So now you can beat this to death with 18th century. So this is like, the answer is the Bessel function. So remember, what is the Bessel function? Is the solution to the differential equation. So this is the answer. The answer is the solution to this differential equation. By the way, it obviously satisfies this. Okay, so there, okay, let me. So this object must also satisfy the equation in V. So when you subtract the two ODEs, you go back to the kinematic constraint. So it's not a generic solution of the kinematic constraint. It's a very special solution that solves a pair of ordinary differential equations. So you go from the wilderness of solutions of PDEs to solving ordinary differential equations, just like the Bessel equation. It's beefed up, it has some source. Okay, the answer is more complicated, but it's essentially the same. The only thing I have to tell you are the boundary conditions, which I alluded to in the colloquium. So remember this operator. So this becomes singular whenever the coefficient of the highest order derivative goes to 0. So delta u has u squared 1 minus u squared d2u minus 2u cubed du. Okay? Now, the boundary conditions, you can impose them at u equals plus or minus 1. And funny enough, there's a singularity that you didn't ask for, but symmetry forces you to have it, which is at u equals 0. But this is an output of the computation. U equals 0 is what? It's S goes to 0. So, but when S goes to 0, it's when the exchange momentum is very, the exchange wavelength is very long, and the singularity is coming from particle production, because cosmology is putting this particle on the mass shell. It doesn't have flat space analog, okay? It's cosmological particle production. So that's why it's forced upon you. U equals plus or minus 1, what does it mean? It means S equals K1 plus K2, and S plus K1 plus K2 equals to 0. Okay? So this, the equation is telling you that the answer wants to blow up when you are in this collinear singularity. And you tell it, no, 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 no. Okay? So you want it not to blow up in this limit. So you impose, there's a logarithmic singularity, log of S minus K1 minus K2, and you want the coefficient to be a big 0, okay? So this is one boundary condition, and the other one is related to the sum of the energies that flows into the vertex. S plus K1 plus K2 is the sum of the energies that enters here. So you normalize it, you normalize using 3-point data, because you can build the coefficient of the singularity using the 3-point correlator, okay? It factorizes. So you build it using factorization. And you're done, okay? You have boundary conditions, you have an ODE, you go to your favorite textbook on ODE, and you can just solve it for every value of moment. And then you can produce a plot. The plot looks like the thing I showed you before. Something like this, okay? It has some decay. You can fit this part here with smooth functions that look like this. And then as u goes to 0, you see these oscillations. They go like u to the I m over h, roughly, plus complex conjugate, okay? So that's it. So that's the form of the answer. But you can compute it, very beautiful, everything works just fine. And in the end, the workhorse is to not, I mean, you could have said, why don't you just write down the time integrals? Well, maybe I didn't stress this point, but remember what was the solution of the wave equation for a massive particle in ds? It was some Hankel function. So the propagator is a product of Hankel functions, a generic mass. So you'd have to integrate a product of nested integrals of products of Hankel functions. And that's the reason why we went through all this pain to find this nice set of differential equations. Okay? So I see that I'm bad. I have half an hour. Okay. So let's do something fun. I'm done with my institutional duty, so I'm going to do something fun. And it's if you're confused by the end, I did my job. So, but I think it's pretty cool. So let me entertain you. So see this last half hour as entertainment. So this was educational, I hope. So when we found this equation and solved it, people were like, oh, but you can only do it because, as usual, you know, people, okay, whatever. But just because there's a lot of symmetry. Then you can relax symmetry. You can make the model more realistic. For example, you can make the inflaton have a non-zero speed of sound. There's a long story about how that enhances the signal, okay? But it boosts symmetry. You lose a very powerful symmetry constraint. And it turns out that after some work, there's also a differential equation that depends on boundary momenta. You don't need to do time integral. But what if you do this? What if you do that? And what if you change the background? And it turns out that in every case, there is a boundary differential equation. So the question is, are there always boundary differential equations? And to which the answer is maybe. Okay? So let me offer you something to that extent. I alluded to it in the colloquium. So you take a little model. The model is very crude. So that is somewhat close to the real world, but this is very far. So you take a conformally coupled scalar. r over 12 phi squared, and you add the phi cubed, okay? Phi cubed. Now, I'm gonna take the scale factor to not be de Sitter. So for de Sitter, it goes like 1 over eta. I'm gonna write eta to the minus 1 plus epsilon, okay? So this is because for epsilon going to 0, it looks like inflation, and epsilon equals 0. So epsilon equals 0 is ds. Epsilon much smaller than 1 is inflation. But this describes other cosmologies, okay? Even non-accelerating ones. So epsilon equals, well, epsilon equals minus 1 is flat space. Epsilon equals minus 2, I always mess this up. So one is matter domination, one is radiation domination. Which one is which is left as an exercise for the reader. I don't remember which one is which. But in any case, the interesting cosmologies, they fit into this. So it's not entirely crude, but I'm adjusting the mass. So I'm cheating because I'm making the mass be time dependent, depending on the cosmology. That's because then the propagator is very simple, because the classical mode function is just going to be eta to the 1 plus epsilon e to the I k eta. Okay? That's not to say that the correlation functions in this model are trivial. So what do the time integrals look like in this case? So what do the time integrals look like in this case? So in this example, there are 2 time integrals, but it turns out that it's kind of neat to Schwinger parameterize the time integral and integrating frequency space instead of in time explicitly. But there are 2 time integrals to do, and in the end, this object is given by this formula. So bear with me. Bear with me. Okay, so what is big X1 is 1 over U. Big X2 is 1 over V. And Y is 1. Okay, so sorry. So I just have to change notation again. So these are the, and what is this? Does this remind you of something we discussed? It's just the perimeter story. Okay. So it turns out that the claim is that the cosmological integral. I forgot to tell. Where's the cosmology? Cosmology is here. You're like, where's epsilon? You should be asking. It's here. Okay. So what does this look like to you? Should look like a loop integral, right? You have some propagators. You have some measuring dimensional regularization. So it looks, we massage it so that it looks like a loop integral, even though you're doing things at 3 level. And the claim is that the FRW wave function, it depends on epsilon, is going to be the integral. You take the wave function in flat space, this story of the perimeters, and you promote all the outer perimeters to big x's, xi plus little xi, and you keep the diagonals untouched, yij, and you integrate that again against dxi, xi to the epsilon. Okay? So for example, that double exchange diagram, this guy here is x1, this guy here is x2, this guy here is x3, this is y12, this is y23. Okay? So remember that formula that I wrote with the bunch of perimeters and sum of two terms. You take that big formula. There are three such big x's. You shift all of them by little x, and you integrate that 3 times. So you can bet that that function is pretty damn complicated. And you'd like to find a way of determining it. So these integrals are hard. But then our QCD friends have dealt with this for ages. So they're like, ha, ha, ha. You just use twisted cohomology and the Laporte algorithm, integration by parts, and then you get differential equations, okay? So there is a huge set of techniques that you can use to tackle this type of integrals. So let me give you a flavor. Oh, this is kind of beautiful. It involves some highbrow math called twisted cohomology. Twisted cohomology in my mathematical Neanderthal brain just means integration by parts and partial fractioning. So this, I think we can all agree we understand. So the idea is very beautiful. It was developed by, I think, Aomoto, a group of people in Japan that wanted to generalize the hypergeometric function, and also this integration by parts method. Okay. There are lots of people that developed this, and I, like Polyakov, I'm not ready to give the credit properly. So let me explain the idea. So the point is that if you, let's look at this example. If you go to the integration domain, I forgot to put the integral run from 0 to infinity, okay? Because I'm integrating over frequencies. So if I go to little x1, little x2, I'm really integrating here. But the beautiful story is that the singularity structure of the integrand kind of determines everything there is to know about the functions. So where is this integrand singular? It's singular in 5 different lines. So it has a cut at x2 and x1 equals 0. Because of this, I'm working at generic epsilon. As usual in GMRAG, you work a generic epsilon, you throw away boundary terms, and you hope you land on your feet when you set the value of epsilon that you care about. So this is what we're going to do. And it's also singular at x1 equals minus something, which is here. At x2 equals minus something, which is here. And at this line, which is here. Okay? So this is the singular locus of the integral. So the first idea is consider all such integrals. So you take the integral dx1, dx2. You never touch the measure. So this measure is called the twist. That's all. It's twisted cohomology. And then you allow for any denominator that is integer on these 5 lines, okay? And 2. So you build a space that is labeled, it's 5-dimensional. It's labeled by 5 integers, or 5, yeah. And 1 and 2 and 3 and 4 and 5. You're interested in the case 0, 0, 1, 1, 1. But now you consider the space of all of them. So you didn't know one integral, now you don't know infinitely many. So that doesn't look like progress. That's the first idea. But these people are smart. So then the point is that they are not independent. Because integration by parts and partial fraction. So for example, if I take a total derivative outside, then I expand this out, I'm going to get a non-trivial relation among different integrals when I shift these guys by units. You see that? If I write partial fraction is even simpler. If I write, for example, 1 over x1 minus 1 x1 plus big x1 plus y, I get big x1 plus y divided by the product. So I can write something with n1 and n3. I can write it in terms of two terms, where I reduce in each of the term the n1 weights and the n3 weights by 1 unit. Okay? So this is pretty dumb. So like, so what? What's the big deal? Well, then come the theorem of these wizard mathematicians. So the theorem, which I actually have no intuition for the proof, but I know it's true because I checked in zillions of examples. So, and of course, the proof doesn't really work out an example. Good mathematicians form. You just say the theorem is true, and it is. So theorem, all integrals form finite dimensional vector space. So if you know a few of them, you know all of them. So now, okay, that's good. So you had one problem. Now you traded for infinitely many. Now you go back to finitely many. So that's the first part. The dimension, and that's kind of mind-blowing. The dimension is the number of bounded chambers. So you look at this integration domain, and now you count how many bounded regions. There was this question about the Euler character. So you look here, and let's count. So how many bounded regions do we get? 1, 2, 3, 4. So the dimension here is 4. So if I know 4 integrals, I know all of them. Okay? And now I'm done. I found differential equation. Why? Take your 4 favorite independent integrals. Let's say you want the original SAIFR W. Now you take 3 others, psi1, psi2, psi3. Okay? They depend on x1, x2, and y. Now take a derivative. Take a derivative with respect to x1, for example. So what happens? You just shift these exponents, right? If you hit x1, you raise this by 1 unit, and so on. So all you do when you hit this with x1 is you produce other integrals in the same vector space. But this is a basis of the vector space, so you're just doing a basis change. So there's going to be some basis rotation. And that's it. So this is the differential equation, okay? So now, very good, very nice. Oh, so very good, very nice. And the cool thing is that this matrix A is very special. I mean, this is a 4x4 matrix, so if every entry of the matrix is a messy function, so okay, so you produce a useless differential equation, so that's not very nice. But, well, you know, nature is kind to us sometimes. And here it's being kind. So let me tell you what the equation looks like. For this, I really need my cheating. Okay. And, right. Right. Okay. So now to keep track of the differential equation, I need some notation. Okay, so that's it. I mean, this is pretty cool, no? What the hell? Like, I mean, I think it's crazy. Okay, but let me tell you that once you know this, I mean, this case is nice. You can do it, but then you get into trouble real quick if you just follow math. If you go to the next example, starts to become hard to visualize, as you can imagine. So the next example involves 3 integrals. So the next example, there's this double exchange, so there are 3 times to integrate over. So there's this psi flats, what I wrote before, where I shift big x1 plus x1, big x2 by x2, big x3 by x3, and I keep the y's untouched. So this is in 3D. Okay. So now you go to 3D, I tell you. I tried, if you're good at visualizing things, I would love to see, I've been asking people for years, I would love to see a picture of this. So you're in 3D, there are 9 planes. Okay? So 6 of them carve up a cube. 6 of them carve up a cube. But unfortunately, there are infinite planes. So far there's only one bounded chamber, but the planes go through infinity. Now there are 3 more. And the 3 more make all hell break loose here. So one of them just carves like this, parallel. Okay, so it's just this plane. So it goes infinitely in this direction. Then the other plane does the same for say, these facets here. It goes parallel. And the third one cuts diagonally, like this. Okay. The third one cuts like this. So how many bounded chambers you think I get? Maybe I told you this so you know the answer. If you paid attention to the colloquium, you know the answer. Do you know how many bounded chambers? How many do you think? So I had just one. I had just 3. Where are 3 more cuts among friends? So how many bounded regions do you get? No, that's the right answer to another thing, but that's not the number of bounded regions. The answer is bigger. It's 25. If you can build a Lego of this and send it to me, I'll be forever grateful. Okay, I've tried Mathematica. I asked people that do 3D printing and so on. Okay, fine. I spent an inordinate amount of my time looking at these 25 blocks abstractly. But it turns out that only 16 of them are explored by the differential equation. So if you write a 25 by 25 dimensional matrix, it turns out that if you put the wave function here and the correct number of 15 cousins, you get a closed 16 by 16 block that doesn't talk to the others. Okay? That's not surprising that it can happen because, for example, if I take in this space, if I take an integral that looks like this, x1 plus y, x1 to the epsilon, x2 to the epsilon. I mean, formally this blows up, but of course, this is not going to talk to things that have singularities in these other positions, okay? So, but it's more interesting than this. I'm just saying that it's not necessarily the case that any integral in this family needs to talk to all the others in the basis, okay? So there's only 16. But, okay, the next example, of course, then I can't visualize, is in 4 dimensions. There are, I think, 12 planes. So you slice 4D space with 12 hyperplanes, and you get something like 200 and something, 202, I forget. And here you get 64. So that's, so now you're a smart kid, so you know what will happen. So you always multiply by 4, while this grows factorially, okay? So the math hammer is very powerful, but it's total overkill for this problem. But of course, once you get to a 64 by 64 dimensional system, you start to lose some intuition of what's going on, right? But it just so happens that the matrix is very sparse. Most entries are 0, and the non-zero entries have some sort of life. So this is what I want to describe to you in the last 10 minutes. The life of the entries of the matrix. And this life feels like some sort of flow in kinematic space. So we call it kinematic flow. I want to give you a flavor of what it looks like. Maybe I will do that by introducing some notation, then asking you to suspend belief in the laws of physics for 1 second, and then we come back, okay? So it's more interesting if we do the double exchange case, okay? So the double exchange is like this. There's x1, x2, x3, y12, y23. And here, because there's only 2 propagators connecting them, then it's easier to exchange this by just the 2 propagators. This is in kinematic space, okay? It's not propagators in space-time. Here I put y12. Here I put y23. It's related to the exchanges. And here I put x1. Here I put x2. Here I put x3. So I need a little bit of notation. I'm going to put little crosses here. And the crosses are to take into account that sometimes you have this funny collinear singularities. So these denominators appear, the ones that I ultimately forbid, but they are there in the differential equation. So now I'm going to draw tubes in this kinematic space. And the tubes tell me about denominators. So for example, if I draw a tube like this, then I associate to it a denominator that looks like 1 over x1 okay, so the rule is if I encircle across, I put a minus, okay? So this is minus y12. So let's do another example. If I do this tube here, I write 1 over x1 plus y12. Now I do one more example, and then you're going to be specialists. So if I do this, for example, and I do a tube like so. So what is this tube? It's 1 over x2. The y12 comes with a minus, and the y23 comes with a plus. Okay? So very, very clear. One more example. What if I do a tube like this? 1 over x1 plus x2, and then y23. Even though I enclose this guy, now I enclose the whole tube. So I only count the vertices, okay? I don't count this y12, but it cuts through this edge. So I count y23 with a minus sign. Okay? And so on. So now I'm ambitious. I want to package all differential equations. So of course, if I take derivative with respect to x1, I'm never going to see denominators that depend on x2 and y alone. They must always depend on x1 and other stuff. But the cool thing that happens is that I can I can think of 1 over as a d log. So I can write this as d log. So that's to say this is a denominator that will always appear when I take a derivative with respect to x1 or y12 with opposite sign. Here, this denominator will appear whenever I take a derivative with respect to x1, x2, or y23 with signs given like this, okay? So it's just a tiny, it's just because I want to kill all birds with one stone, not to talk about the differential equation in every variable. You just bundle them up in these forms. Okay, so this is just a vector that has the derivative with respect to x1 in the x1 direction, the derivative with respect to y12 in the y12 direction is 0 in the other directions, okay? Now, I will tell you 2 rules. We're getting there. I'll tell you 2 rules. 3 rules, sorry. So all bases of rule 0, 0th law of kinematic flow, all basis functions follow from total tubings So the rule of the game is I tube the kinematic space, and I don't want the tubes to overlap. So let's see how that works. In the simplest example, which is single exchange, there's only a diagram like this, right? There's x1, x2, and y. So let's build the 4 functions. I need total tubing, meaning I need every ball to be encircled by a tube, and the tubes must not overlap. So number 1 is this. Number 2 is this. Number 3, this. Number 4, this. Okay? So the tubes must always enclose the little balls. The cross is not so important, but there are different tubes where they are encircled and do not encircle the cross. So this is the 4 bases. So this is the zeroth rule. So if you do this exercise here, you should get 16. So that's where the 16 comes from. It's all possible tubings of this double exchange graph. Okay? There will be interesting tubes because there will be tubes that encircle only this guy on the left, only this guy on the right, both at the same time, only the guy in the center. So it's not entirely trivial to do it, but you get the gist of it pretty quick. So this is the first thing you do. And now you built a basis. And now I'm going to tell you 2 rules. 2 rules. I mean, we proved that, I mean, when we discovered them, it was black magic. But then we realized it was pretty dumb to prove them, and then we wrote another paper proving them. But we thought it was magic. But of course, it was just mathematics, but of integration by parts and partial fractioning, okay? Done in the right way. But now there are 2 rules. First rule is activation. So let me read the rule for you, okay? So you pay attention. Me and not at the board. So you color all tubes one at a time. Then the denominator, it multiplies. So when you color a tube, it gives you a denominator, okay? It multiplies with coefficient determined by the circle enclosed, the original function. So you activate, so for example, here there are 2 tubes. You activate one at a time. So when you activate this guy, you generate 1 over x1 plus y. When you activate this guy, 1 over x2 plus y. And they multiply the original function. So that's the activation. So you're just getting something proportional to the original function, but you activate 1 tube at a time. So here there are 2 tubes. You get 2 denominators doing that. And the second rule is merge. So the tubes can grow. So when the tube encircles a cross, it can grow and merge. So for example, when I kick this tube here because it encircles a cross, it can grow and merge and form this bigger tube here. So and then you can get something that multiplies the merge function with some coefficient. So the second rule is merge. So let me show you how it works in an example, and then we'll stop. Let me do, so of course I could do the 16 by 16 matrix, but you'll probably murder me by the end of it. So I'm going to do one example. One of the 16 lines, I'm going to take the function that is associated with this tubing here, because it illustrates all the points. This. Okay? So this is one of the 16 functions. I associate a function to this total tubing. Notice that the tubes do double duty because a complete tubing labels a function in the vector, and when I circle one at a time, I produce a denominator. So they know about the function, they know about the denominators. So now what do? If I take the total derivative of this function associated to this tube, I write, first of all, I activate each tube one at a time, and each tube is a denominator, okay? times the original function, psi. So what is this? It's 1 over d log of x1 minus y12. This is d log of x2 plus y12 minus y23. And this is d log of x3 plus y23. Okay? So it produces 3 denominators. And then there are 2 ways. So you see, these tubes enclose crosses. So there are 2 ways of merging. So the first merge is between these 2 tubes here. Okay? So I can make this tube grow and encircle this one, or I can make this tube grow and encircle this one. So we treat one at a time. So the first merge, so these are the 2 tubes that merge. There's some story about why the relative sign is like this that I'm not going to tell you. And they multiply a new function that is associated with a different total tubing. Remember, every basis function, so this is an off-diagonal term in the differential equation. These tubes merge, so there should be a function associated with this tubing here. And then there's going to be times another function that is associated to the other type of total tubing. So when these guys merge, I get this and this. Okay? So this is an entry. There are 16 entries in a line. Only 3 of them are non-zero. The diagonal one with 3 terms and 2 off-diagonal terms. And you see, every time I go to a given tube, I get bigger tubes. So there's a sense that if I stack all the tubings and they keep growing as I go down, the matrix is going to be only lower triangular, right? It's only going to talk to things that are under a given entry. So in this sense, the tubes are growing. So when I get total tubings, the procedure halts. The fact that this gives an integrable connection in kinematic space and so on is a miracle. Okay? We understand why, but when you stare at these crazy rules, the fact that derivatives must commute and so on is not obvious at all, but it works out. There's only one free coefficient in these rules, which is epsilon, which is the cosmology. So you change the cosmology by changing the coefficient. Okay? So this is pretty cool. And now we're investigating if this works beyond this toy example. And it works for you can draw the craziest diagram you want with 4 to the n entries, and you can draw tubes, and you can predict every entry of a system of zillions of differential equations. Okay? So this is my take on what holography could look like in a cosmological space-time. There are these motions in kinematic space, and with them, you're able to build the cosmological correlator. You're just trading, rescaling one distance scale at a time by slowly destroying the propagators of what's happening in the bulk. So that's what these differential equations are giving you. Okay? So I'm 5 minutes over time. I hope this was chaotic, but I hope you get some feeling of excitement out of this. It's some pretty cool structure that you just follow your nose. You see, you're trying to make these computations practically useful. It's not, I want to, do some very highbrow thing, because you're trying to follow your nose and you want to make these computations practically useful. And then sometimes by accident you run into some structure that is interesting on its own right. Okay? So it's not that we were en route to unravel some geometric structure. And by the way, the question about Euler characters, these functions, they seem to have all sorts of Euler character looking alternating sums appearing here and so on. So there's a lot of things associated to this that I don't understand. And you just follow your nose and this appears. So it seems that nature is trying to give us some hint of how it operates in cosmology. So I'll just wrap up by saying this topic of cosmological correlators is something that there's a lot of interesting new things happening in it. Lots of intuition that come from amplitudes, from conformal field theory. I still feel that it's one of our best hopes of connecting these theoretical ideas about quantum gravity and so on to the real world, to observations. It's still useful to keep a phenomenological eye towards how you could apply this to maybe primordial non-Gaussianities and so on. But it's a very interesting and new theoretical laboratory in its own right. So I hope I gave you some flavor of developments in this field in the past 3 or 4 years or so. And I think that there's still many, many interesting things to do. This was all about tree level. We don't understand loops. We don't understand non-perturbative things. We understand very few things about those. We actually, even at tree level, we don't understand everything, I claim, like things that are related to gravitational waves, spinning particles. There's still work in progress about this. So there are many, many interesting things to work on. So I invite you to join and try to play with these ideas. So I'll stop here.
Okay, questions? Yes.
Thank you. So in the tubings that you draw there, what is the feature that you use to distinguish, for example, the second and the third graph? Because it seems that if you rotate this the other one, and maybe they are related by a symmetry factor. I don't know.
1, 2, 3, and 4. Which
Exactly.
one?
2 and 3.
2 and 3? So here it's, if you want to think about this in terms of the history that gave rise to these diagrams, it's because, roughly speaking, diagram 2, the arrow of time flows like this, and diagram 3, the arrow of time flows like that. So they are related by permutation, right? But you permute the kinematic labels.
Okay, but the difference then is the time.
Well, here in kinematic space has to do with the denominators that each one produces. So this one has a denominator that is a d log form on x1 minus y, while this one has a denominator which is d log of x2 minus y, while this one is d log. It's where the minus signs are. So the type of denominators that they produce are they differ by a minus sign. But the physical interpretation of the difference has to do with these two different stories. Yeah.
Thank you.
More questions? Yeah.
Hi. So, is there a particular reason for the toy model that you have? Could you have like, because the toy model when you start this discussion here, it has this time-dependent mass term, right?
Yeah.
Does this work for other toy models, or is this?
Yeah, I think so, but nothing's published yet. There are other deformations you can do that, for example, will produce massive correlators in de Sitter space. So you can fix the cosmology and change the masses of particles by similar type of game. And the story is more complicated, but it smells like there is a similar structure there. So yeah, I think the short answer is yes, but there's no working example yet.
Right.
So this was just the simplest example where we could, I mean, the original idea was just to see if differential equations existed. But then we found much more structure than just differential equations exist, so we just pushed it. But I think that similar structure probably exists, say in QFT in de Sitter space and so on. So we'll see.
I see. Great.
Anyone else?
You are waiting.
Sorry. My question is related to the previous one. In this procedure, is crucial that the interaction is cubic?
No,
Okay.
it's not.
Great.
Yeah, I mean, the interaction being cubic is nice because the free coefficient up front is the cosmology. But if you what you can do is you can assign to each of these little blobs its own interaction strength. So then there will be alpha 1 here, alpha 2 here, alpha 3 here, and so on. And then this adapts to phi to the n, for example. It's just that the phi to the n will control these coefficients here. So it works for polynomial self-interactions also.
Okay, but the triangulations is more difficult, right? Because
No,
the lines, the internal lines.
Triangulation is the same because I'm working at tree level. So what happens is that you have stuff like this. So the number of external legs is growing, but I'm working at fixed number of propagators. So the triangulation fixes the number of propagators. So the phi to the n alters the number of external legs. So that's the, yeah. If you want to do one loop, then all hell breaks loose, okay? But yeah, I have a student that spent his whole PhD computing this diagram here, okay? So we're going to write this up now. So this diagram in flat space, okay, the analog of 1 over the perimeter thing, this diagram is a sum of 150 polylogarithms, okay? So this, there's lots of beautiful structure of the singularities and ta-ta-ta, but yeah. At one loop, cosmology is very complicated. So everything that we understand is at tree level. So if you change the polynomial interaction, what you end up doing is you just change the number of external particles. Yeah. I mean, of course, yeah, another thing you can do is you can do a more complicated diagram. You can do stuff like this. Right? But then you need to build some very complicated, like, I don't know, you need to make this work at tree level. So like, maybe let me do phi cubes, okay, on these other vertices. So then you need to keep, well, I guess you get the gist of what I'm trying to draw, right? So the kinematic space is going to be very complicated, and but in any case, you can still do work at tree level. And we never publish anything related to this, but these rules essentially work. The number of equations is like 4 to the 1, 2, 3, 4, 5, so 4 to the 5. But you can predict every line by playing these rules here.
At loop level, do you expect it to work like the amplitude game, that you can build the integrands?
Yeah, at the level of the integrand, the story has been worked out and it works beautifully. But the loop measure messes everything up. So we don't know any story to tell at the level of the integrated result. What are the differential equations? That would be very nice. And even at the level of amplitudes, a lot of these interesting constructs like amplituhedra and so on, they are for integrands, right? We'll see. Yeah, so the difficulty is at the level of the integrated result. At the level of the integrand, there's some, you need to update the rules just to take into account that if you put time-ordered propagators in a loop, you get 0, right? Because of time ordering. There's no way to get you get a closed loop. So that's it. If you update this rule, the rules are essentially the same.
So I have a simple question. So the ultimate goal is to find some observables that you can measure and differentiate among different models. Is that the goal? For instance,
I guess it depends on what, I guess for the lectures, yes. For this in particular, I'm just trying to understand the structure of these cosmological observables. It's a mathematical physics question, and I have no idea where this is going to lead us. I'm hoping that there will be some autonomous structure that you can then try to understand intrinsically, like without talking about these diagrams. Right. Some, I don't know, holographic version of cosmology. And I don't know what it will be good for. It's exploratory. It was mostly to try, it was motivated by the need to compute this type of correlators because of application to non-Gaussianity. Yes. But then this is very much beyond any reach, right? So we're just pushing the mathematical physics angle to see where it leads us.
So that's my question. Can you, for instance, for non-Gaussianity, can you differentiate phi cubed from phi fourth, for instance?
Well, yes, I think so. I mean, it depends on what you mean by phi cube by phi fourth. When I talk about phi cube, phi 4, I really mean at the level of the perturbations. Maybe you had, if you had in mind potential, then it's the usual story. It's like it's scrambled in the coefficients of shapes. I think the non-Gaussianity business is about shapes. So you have shapes, and the shapes tell you some physics, and then the coefficient that multiplies a given shape, then you can interpret in many different ways. But I think the shapes have a fairly robust interpretation. So equilateral non-Gaussianity, it's always some sort of self-interaction, some short distance dynamics during inflation. Local, always long distance. And then these types of things are about, oh, how would you see, you know, messengers, how would you see strongly coupled sectors and so on. So that's, I think, how things would fall into umbrellas.
Right.
Yeah.
So what you're doing is that you're going beyond, so you're talking about perturbations, not the potential.
Yes.
So you're going beyond perturbation theory in that sense, because you're considering higher orders in perturbation.
Well, I'm going to higher orders in perturbation, but I'm still expanding around phi equals 0, right? There are interesting questions about the tail of the PDF, very rare phenomena, or what happens. Something I did not talk about in these lectures is what people call stochastic inflation. So for example, if you do literal phi to the 4, massless phi to the 4, for the perturbations, the theory gets strongly coupled. So then you can't trust the tree-level approximation anymore. You need to develop machinery to deal with that Starobinsky developed. But even there, the computation of this type of observables is not being done yet. So for example, phi to the 4 theory, massless phi to the 4 theory, we don't know what the shape of the 4-point function is. Okay? We don't know. Okay. People usually compute 1-point functions of composite operators. That's kind of the state of the art, or maybe 2-point functions. But these type of things where there's kinematic dependence and so on has not been done. And you know, you could wonder that there's some interesting shape that doesn't fit the usual equilateral local and so on. So maybe you can use it for phenomenology. So, but I don't know. So that's the.
Thank you.
Okay, we thank Guy again.
Thank you.